Okay, let's get going this morning. Welcome back, everybody. So last time we were talking about how we can take symmetry operations and express them in terms of matrix notation. And what we want to do today is to develop what are called character tables for different kinds of point groups. The character table is front and center in an understanding how symmetry can be used to explain things like vibrational properties of molecules and bonding and so forth. So the character table, you'll hear this term a lot. It's a kind of a big, scary idea. We're going to try to break it down into its components and understand how character tables are actually formed, and then we're going to use them for the rest of the entire class. So we ended here last time where we had used the transformation matrices, or developed the transformation matrices, for a simple point group. I think we're in C2H here. And we showed how the identity C2I and the reflection operation can be expressed in matrix notation. And what we said is that using matrices, of course, you can do the same kinds of manipulations that you would do just intuitively, and you're going to get the same answer. So if you do a C2 operation followed by another C2, you get the identity operation. And this works out through the matrix multiplication that we talked about last time. What we ended with last time is that if we take the sum of the elements along the diagonal, this is called the character of the individual transformation matrix. And this sum of numbers here, the character gives us a shorthand version of the matrix representation, and we call this shorthand version big gamma. Okay? And so we have, for E, we have 1 plus 1 plus 1 is 3, and so we can write that gamma for the operation E gives us a character of 3. For C2, we have minus 1 plus minus 1 plus 1, that's minus 1 altogether. And so forth. For I, we have negative 3, and for the reflection, we have positive 1. This collection of characters here for gamma gives us a reducible representation that in this particular case explains how x, y, and z, the coordinates at the center of the molecule, transform with the four different operations that we have in this particular point group. This reducible representation is so called because it can be further simplified into components. And we're going to generate what are called irreducible representations, which are the basic building blocks of the symmetry of this point group. So let's do that. How can we further simplify and go from a 3 by 3 matrix to something more simple in this case? Well, we can do what's called block diagonalization. We realize that most of the elements, in fact, all of the elements in this particular case that are off diagonal are 0. They contain no information, so we can just ignore them, and we can block diagonalize each 3 by 3 matrix into individual 1 by 1 matrices, 3 1 by 1 matrices, okay, for each case. So we have 3 1 by 1s here, we have 3 1 by 1s here, etc. Okay, for the others. This first row here indicates what happens to the x coordinate, the second row what happens to the y coordinate, and the third row what happens to the z coordinate, because we're talking about transformation matrices. So we have x, y, and z. We can take these numbers now, the individual 1 by 1 matrix characters, and we can express them in the form of a table, okay? A convenient way to show the information. And this is beginning to show what a character table will look like. Okay? It is a table in which we have columns up here, each column corresponding to a symmetry operation in this case. Okay? Under the columns, each symmetry operation, we have the characters, in this case along the diagonal. So we have for x, y, and z, we have 1, 1, and 1. For C2, we have negative 1, and 1. So that's negative 1, and 1. And so forth for I, and so forth for the reflection operation. At the bottom here, we have the sum of these characters. So 3, negative 1, negative 3, and 1 that we had developed in the previous slide. So this would be called the reducible representation. Each of these 3 rows here are called irreducible representations. Okay? They cannot be further simplified because they're based on the simplest components of these matrices, which are 1 by 1 block diagonal matrices. We also have here the x, y, and z, the coordinate that corresponds to each one of these 3 different rows here. I will explain, of course, this notation in a little bit. But a character table is essentially going to have the symmetry operations as columns. They're actually going to be called the symmetry classes. Just a slight distinction that we'll make clear in a little bit. And along the rows here, we're going to have the irreducible representations for the point group. The point group designation is always given in the upper left corner of the table. So these three rows, as I mentioned, in this case BU, BU, and AU, are irreducible representations of the C2H point group. That's the language we would use. They can't be further simplified because they're just one-by-one matrices. Okay, there's no way that we can get more simple than that. Okay. All right. So who cares? What are we going to do with these things? Well, these individual irreducible representations here, the characters for these individual irreducible representations tell us how these irreducible representations transform for the different symmetry operations. Okay. And in the table, if you have a character of 1, that means that you're unchanged upon the symmetry operation. In other words, you're symmetric. So symmetric and unchanged are interchangeable words here. If you have a -1 as your character, that means you're antisymmetric, or you're inverted upon the symmetry operation. And if you see a 0, that means it's something else. Okay. So let's look and see how this portion of the character table for C2H gives us information about how our different coordinates change with these symmetry operations. Let's use an example. This is the same example that we used before, 1,5-dibromonaphthalene. Okay, so this is a C2H molecule that you should be able to convince yourself of very quickly. We use the coordinate system, the convention that the z-axis is along the principal diagonal of the molecule, the C2 axis in this case. And that means the molecular plane is the xy plane. Okay. So let's look and see, for this particular, let's just start with this one arbitrarily. So for the AU irreducible representation, we see that it transforms like the z-axis transforms in the molecule. So if you look at the identity operation, it's unchanged under identity, like everything is going to be unchanged under identity. For C2, okay, the z-axis is unchanged, right? The C2 is parallel to the z-axis, so flipping 180 degrees around the z-axis does not change the coordinate. So we have a symmetric or unchanged character there. Upon inversion, the positive z goes to negative z, and so we have a character of -1. Indicating that it's antisymmetric. And for horizontal reflection, that also changes positive z into negative z. And so we expect then that upon the horizontal reflection, we're going to have an inverted character, -1. And so that's why z and AU basically have the same symmetry in this particular point group. Okay? We would say that the AU irreducible representation has the symmetry of the z-axis in this particular case. What about these others here? We have two identical irreducible representations here. Both are called BU, and we'll explain why. But you can see why they're identical. It's because they have identical characters. Okay? One is given x, and the other is given y. Okay? We can say that the BU transforms like x and y in this case. So again, we can look at the different operations and see how they transform. Under identity, of course, no change. Under C2, both the x and the y invert, and so we have a -1. Under inversion, they both invert, and so we have a -1. And under a horizontal reflection, a reflection in the plane of the molecule, neither x nor y change. And so we have a character of +1 in this case. And so we have the BU irreducible representation transforming like the x and the y axes in this particular case. That's what you can read, that's what the character information here tells you, okay? How these individual irreducible representations transform under the different symmetry operations. Because we have two BUs and they're exactly the same, they have the same exact characters, we just merge them together in the table. So instead of having two rows, we just have one row that's called BU. And we indicate that both x and y transform this way by just putting x comma y. Okay? Indicating that both the x and the y coordinates, or the axes, have the same symmetry in this particular point group. This, of course, will not always be the case. If we chose another point group example, then the symmetry of the x and the y axes could be different. In general, they will be different. Okay, so we have, in this case, part of the character table. This is not the total character table for the C2H point group. But what we've done is shown how you can get two irreducible representations. It turns out there are 4 altogether. But we can get 2 of these by looking at the transformation matrices, how x, y, and z for the molecule transform under the different symmetry operations. Okay. What we want to do is show in a little bit how we can generate the full character table by starting with the transformation matrices and then using some of the properties of character tables to kind of finish off the problem. So this gets us into the meat here. So character tables kind of as the central focus for the rest of this lecture. Hopefully we'll get to the first application of character tables and symmetry at the end of the class today. Okay, so we were working with C2H, and we showed two irreducible representations, which is basically half of the character table for C2H. This is the full character table for C2H. This is what you'll see if you look at the back of your book in Appendix C, I think, is where these character tables are. And this is the same format that you'll see in almost any reference guide that has character tables. It talks about molecular symmetry. Okay? You can see that we've got basically 4 different sections of the character table. Okay? So the first section, the characters, and then these other 2 columns here. So we want to understand exactly what this is telling us. Okay? So we're going to go through it piecemeal. Okay? What a character table is, it's simply a list or a table of the complete set of irreducible representations that's shown here in these rows, okay? And the symmetry classes, which are shown in the columns. So it's the characters for every individual symmetry class for each individual irreducible representation. Let's start by understanding this notation over here and what this tells us about the characters. So these guys here are the irreducible representations, and they're given a label that tells their symmetry. The label is called the Mulliken label for the representation. And it has the following flavor here. So if you see A or B, and in this case we see only A or B, what this tells you is you have a 1-by-1 representation. Remember we had for C2H only 1-by-1 matrices along the block diagonal. If it's A, that means it's symmetric with respect to the principal axis. If it's B, that means it's anti-symmetric with respect to the principal axis. So it tells you right away what the character is for the principal axis. You can see the A has a 1 and the B has a -1. Okay, it's either symmetric or anti-symmetric. Sometimes you'll see an E instead of an A or B, and sometimes you'll see a T instead of an A or B. If you see an E, this means that you have a 2-by-2 matrix. Okay? And the character under the identity operation is then going to be a 2. And if you see a T, that means you have a 3-by-3 representation. And that means that the character under the identity operation is going to be a 3. Okay? We'll see this example in a little bit, okay, when we talk about a molecule with the C3 axis. Okay, in addition to the A and the B, or the E and the T, we have these subscripts. In this case, we have G and U subscripts. Okay? For point groups that have inversion like this does, right, C2H has the inversion operation, the representations are labeled with the subscript G, which is gerade, German word, or ungerade for U, to denote whether they're symmetric or anti-symmetric with respect to inversion. So you are gerade or G if you have a symmetric relationship with inversion, and you're ungerade or U if you have an anti-symmetric relationship with inversion. So you can just look at the Mulliken label and tell right away what the characters have to be in the character table. Then, of course, there are character tables with more than just 4 rows and 4 columns. There's much more complicated point groups with a lot more symmetry classes. In those cases, what you'll see are additional labels on these Mulliken symbols. Maybe a 1 or a 2 or a prime or double prime, things like this are going to pop up. And if they are present, these additional subscripts or superscripts typically indicate the symmetry with respect to the next operation after the principal axis and after inversion if it's present. Okay? So you might have a 1 if it's symmetric with respect to a reflection plane that's farther along in the character table, a 2 if it's anti-symmetric with respect to that reflection plane. The bottom line is that what we want is a simple labeling scheme that tells us kind of immediately what the symmetry is of that particular irreducible representation. So just at a glance, we can tell the basic flavor of that particular representation.
What do you mean by symmetric to the inversion?
So it's a mathematical definition. So under inversion, does the value x, y, or z invert to its negative value, x, y, or z? Yep. So you can see here, there's a bunch of stuff that we're going to get into in a second, but you can see if you look at the z or the x and the y axes, those are all anti-symmetric with respect to inversion because as we would expect, if you invert, x goes to negative x, y goes to negative y. Z goes to negative Z. But some of these others that have these R symbols, which we'll talk about in a second, are symmetric with respect to inversion. Okay. We'll get to that in a bit. Okay, so we understand a little bit about the Mulliken symbols that are used for the irreducible representations. What about these last two columns here? Okay, these last two columns indicate functions that have the same symmetry as these respective irreducible representations. The first column are linear functions or rotational functions. So linear functions like x, y, and z. RZ, Rx, Ry mean rotations with respect to those individual axes. So rotations around the z-axis, for example, would be Rz. And the second column here are the quadratic functions, right? Those that combine x, so x squared, y squared, z squared, xy, xz, and yz. Why do we care about these particular functions? It's because these functions here, for example, the quadratics, these contain the elements of the d orbitals, right? So if you remember d orbitals, you have dxy, dxz, dyz, dx squared minus y squared, dz squared. Those are exactly the same functions that are shown here. This is so that we can tell at a glance what symmetry the d orbitals have, the individual d orbitals have in this particular point group. Okay. Why do we care about x, y, and z? For two reasons. X, y, and z tell us about translations, movements of the molecule through space. They also tell us about the symmetry of the px, py, and pz orbitals. And why do we care about rotations? Because this tells us the symmetry of the three different possible rotations for a three-dimensional molecule. So we can assign which of these individual irreducible representations have the symmetry of a rotation for this particular object. Okay, so let's look down here. The last two columns, as I said, are these functions. Okay? In this case, because we have an inversion center, the functions are at the origin, so at the inversion center. Let's look at a couple of different molecular orbital examples here, or atomic orbital examples. So here is the x squared minus y squared d orbital. Here is the dz squared d orbital. You can see that in the character table here that we're trying to understand, x squared, y squared, and z squared are all located in the same row. It happens to be the AG, right, representation. So what we're saying is that the x squared minus y squared and the dz squared have the same symmetry in this particular point group. And let's see that. Okay? So let's look at the individual symmetry operations. With respect to E, of course, nothing changes. We're symmetric. With respect to C2, you can see that if you do a C2 along the z-axis here, which is coming out at you, you get the same object back. And if you get, in this case, the z-axis is up and down, if you do a C2 with respect to that, you also get the same object, right? No inversion. So that's why we have a character of +1. Upon inversion operation, what happens to this guy? This particular x squared minus y squared orbital is unchanged, right? The two negative lobes just interchange and the two positive lobes interchange. So the thing is not inverted, it's not reversed in its polarity. Okay? The same thing for the dz squared. The positive lobes interchange and the negative ring kind of just dances around and doesn't change. And under the horizontal reflection operation, same deal. Horizontal reflection is in this plane, so that's unchanged, and it's in the xy plane here, so that's also unchanged. Okay, the object is just multiplied by +1 in that sense. Okay? So that's why those two orbitals transform as AG. Okay? And that's exactly what we can just read right off the table. That's one of the powers of the table. We don't have to think very deeply. It's all there for us to see. Okay? It's all in plain sight. What about the pz orbital? Well, the pz orbital has different symmetry. We can tell what the pz orbital is. We just read it right off the table. The pz orbital must have the same symmetry as z-axis, and that's going to be an AU representation. Let's prove to ourselves that that's true. Under E, nothing changes. Under C2, nothing changes because that's along the z-axis, which is parallel with the lobes here. Under inversion, what happens? Under inversion, the positive lobe, let's just call that this dark lobe here, jumps up here, and the negative lobe jumps down here. The thing has been multiplied by -1, so it's anti-symmetric. Okay? That's why we have a -1 for the character. And under the horizontal mirror plane, right, that mirror plane is in the xy plane, and so again, we interchange the positive and the negative lobes. And so the function has been multiplied by -1. It's anti-symmetric with respect to this horizontal mirror plane. Okay? So you can kind of get a sense for how the character table can be used and how the characters come to be, right? So it all should be self-consistent. We do the same thing with the px and the py orbitals, and we should be able to read these characters off from those different symmetry operations. Okay, so if there are any questions at this point, yeah, go ahead.
For the quadratic, so why don't you write x squared minus y squared, because that's the orbital actually we're talking about. Instead of that, you wrote actually x squared and
Yep.
y squared. Right?
Yep. So the question is, why not just put x squared minus y squared in this function? The convention here and the idea is that any linear combination of these functions also has this symmetry. So you could have x squared plus y squared, x squared minus y squared, x squared minus z squared, and all of those linear combinations would still have AG symmetry. So it's just to make it more general. Because there may be instances that you care about other things just than the real space versions of the d orbitals. Yep. So any linear combinations of these functions and linear combinations of those functions are still good. That's why.
If you're given gamma and it gives you a value of 1 or negative 1, is it inconclusive as to which ones are negative 1 or 1?
It is. Yeah, it is. And in some cases it doesn't matter, in some cases it does. We'll show how you can take a gamma and reduce it to its irreducible parts. Yeah. That's coming up very soon. Okay, other questions? Okay, so there are some rules about character tables that we need now to understand. And these rules come out of group theory. Again, we're talking about the results, we're not talking about the derivations. So when you look at a character table, this is the full character table in its full glory. The total number of symmetry operations, as we've already said, is the order h. Okay? In this case, we have 4. Right? So h is equal to 4 for C2h. We already know that. Operations are going to belong to the same class, the same operational class, if they are identical within coordinate systems that are accessible by a symmetry operation that's present in this group of symmetry operations. One class of symmetry operations is listed per column. It turns out in this particular example that there's only one symmetry operation per class, and so we have only an order of 4, and we only have 4 classes. Okay, this is a simple example. We'll show in a second when we have the number of classes not equal to the number of symmetry operations present in the point group. But we always list the classes, not just the individual symmetry operations in the character table. So we'll come back to that point in a second. The number of irreducible representations for any point group is the same as the number of classes. So in other words, we have a square table. The number of rows and the number of columns is the same. In this case, we have 4 columns and we have 4 rows. This is always true for character tables. We always have one representation that's totally symmetric. In other words, all the characters are positive 1. So our totally symmetric representation is the AG in this particular point group. You can see we have characters of 1 all the way across. Okay. This is a helpful rule. Allows us to actually build the character table because we can always know that at least one of them is totally symmetric. Okay, and then we have a certain interrelationship for the order with the characters in the table. And the following 2 relationships hold. So the order is related to the characters. The characters are usually given the Greek letter chi, okay, in the following 2 ways. So the order of the overall point group is equal to the sum of the characters under the E operation squared for each individual irreducible representation I. So I here refers to the irreducible representations AG, BG, AU, BU. Chi is the character under E. That's what this notation tells us. And we square each of the characters, we add them all together, and we better get the order. Okay? So let's look at this for this particular example. All we're doing is taking 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. And that gives us 4, and that is in fact the order for this particular point group. Okay? So that has to be true. And we also have a relationship that's horizontal. Okay? The order has to equal the sum of the characters for all of the different symmetry operations squared, okay, for any individual irreducible representation. So we can just choose a random irreducible representation and prove that this is true. Let's just choose AU. So we have 1 plus 1, we have 1 times 1 plus 1 times 1 plus negative 1 times negative 1 plus negative 1 times negative 1. That gives us also 4. Right? Pretty trivial. But this always has to be true for a character table. For the E and for any arbitrary irreducible representation, these equations must be met. Okay? And then finally, there's one other very important rule for character tables, and that is that the individual irreducible representations are orthogonal to one another in a mathematical sense. They don't have any component of one in any of the other irreducible representations. Mathematically, what that means is that if you take the sum over all of the different symmetry operations of the product of the character in that particular symmetry operation for irreducible representation I, multiplied by the character for that operation of irreducible representation J, sum them all up, you have to get 0. That's the mathematical definition of orthogonality in this context. So what does that mean? You can just choose any two random irreducible representations in the table and do the sum of the products, and you better get 0. Okay, so let's look at the first two maybe. We've got 1 times 1 plus 1 times negative 1 plus 1 times 1 plus 1 times negative 1. That's just 1 minus 1 plus 1 minus 1 equals 0. Okay? And that's true for any combination of two irreducible representations. These rules are, as I mentioned, coming out of group theory. They're super handy, of course, for building a character table, because you can just make sure that all these rules are satisfied. Once you've done that, you've got your character table. Okay? So let's see how these rules can help us build the C2H. We've shown what the C2H result is, but we haven't actually arrived at it ourselves in an honest way. What we ended up with last time, just based on transformation matrices, is we had two irreducible representations that we were able to generate. But we know from the rules of character tables there must be two more, because we have 4 different symmetry operations or symmetry classes. So we're missing 2 irreducible representations. How do we find them? Well, we know there must be 4, and we know that 1 is totally symmetric. So immediately what we find is one of them, right? The AG, the totally symmetric representation. That must have characters of all 1. And based on the characters here, we can assign its label, right? It must be A because it's symmetric with respect to the principal rotational axis. And it must be G because it's symmetric with respect to inversion. Okay? We have another one in red here that we don't know yet. And so by the process of elimination, we can figure this out using the rules. Okay? So which rule would we want to use? Well, the 4th representation has to be orthogonal to all the other 3. And the 4th representation has to have a character under E of 1, just like all of them do. Okay? And so we have an unknown where we know that this is 1, but we don't know what these 3 characters are, but we do know that the whole thing must be orthogonal to all the other irreducible representations. So how can we do that? Well, the quick way to tell is you can look down here, okay, at these other 2 representations. They both have 2 negatives and a positive, right? 2 negatives and a positive. These first 2 are negative. These last 2 are negative. So I bet you this one has to have a negative in the first and a negative in the third and a positive in the second. And that's going to give us a totally orthogonal irreducible representation. And so that's what's shown here. We have a character under C2 of negative 1, a character under I of positive 1, a character under the reflection operation of negative 1. And that's going to give us a BG irreducible representation that is totally orthogonal to all the others, the other 3 in the character table. How do we know it's BG? It's negative 1 under C2, and it's symmetric with respect to inversion. So that means B and G. And you can see that we've got different characters for all 4 irreducible representations. We have a 4x4 table, as we must have. And you can do those sum rules, vertical and horizontal, sum of products rules, and they'll all work out. So that's how we can generate a fairly straightforward character table, in this case just 4x4, it's not too burly, right? From the transformation matrices and then using our rules for character tables. Questions about how we did this? I'm sure there are many questions as to why we're doing this, but those will become clear, I promise. Yeah.
Can you explain again one more time what you mean by symmetric with respect to inversion?
Yeah, so symmetric with respect to inversion means that when you perform the inversion operation, the object is multiplied by +1. It doesn't change. The polarity or the positive and negativeness of the different parts of the function don't change. So if you go back here, for example, these guys are good examples of symmetric with respect to inversion. Right? So you can see that the negatives stay negative and the positives stay negative or positives stay positive under inversion. Yeah. Yeah.
So does that mean when it's anti-symmetric to inversion that it technically doesn't have an inversion center?
No, it does not mean that. So it means that when you do the inversion operation, the object becomes negative of itself. That's what it means. So you can see that here. If you do inversion with respect to the PZ, the positive and the negative lobes interchange. It's like you took the function, right? The orbitals all have functions corresponding to them, and you just multiply the function by -1. That's what you're doing. So it's anti-symmetric. It's not asymmetric, it's anti-symmetric. Anti itself, yeah.
Sorry, just to clarify, when we're referring to the symmetry of the orbitals, we're referring to the shading on them, correct? So,
Yeah, so the easiest way to look at the symmetry of an orbital is to look at the positive and the negative lobes, right? And so that's why they're shaded in the way that they typically are. Right? So the shading is to indicate positive and negative parts of the wave function. Okay. Okay, so the C2H, a nice character table to build ourselves, fairly straightforward. Let's look at another fairly simple example of a character table that has a couple of different new features to it. Let's look at the C3v character table. We should be able to recognize a C3v molecule and list all of the symmetry operations that correspond to C3v. So such a molecule is ammonia. Okay? And ammonia here is C3v because it has a C3 axis, right, down this line here. There are two operations that correspond to that, right, the C3 and the C3 squared. And we also have vertical mirror planes, right? We have 3 of them, each one passing through a nitrogen and a hydrogen, right? 120-degree rotations around. So altogether, and there are no other symmetry operations, so altogether there are just 6 symmetry operations. You can see there's 1 plus 2 plus 3. In the character table, they're grouped into classes of operations. We don't list all of the individual symmetry operations. We group them together according to their similarity. The 2 C3 operations are identical. They have identical characters. And the 3 vertical mirror planes are also identical by symmetry. Okay? So they get grouped into the same class. And so in the end, what we have is a 3 by 3 character table. Okay? So one new feature is that we have classes here that have multiple symmetry operations in them. Okay? That was not the case with the C2H. The other thing that's different about this particular character table is this guy down here. We have an E irreducible representation. And you can see that for the E irreducible representation, that means that it's a 2 by 2 matrix, and that means that it's got a character of 2 under the identity operation. Right? So this is identity operation. This is irreducible representation E. Unfortunately, this is the notation. It can be a little confusing because you've got 2 E's. Right? Just remember that this is always the symmetry operation. Okay, if we wanted to build the C3v up using the same approach that we just used for the C2H, what we can do is find that we can get the A1 representation and the E representation from the transformation matrices. We have 3 different kinds of symmetry operations. So we have 3 transformation matrices, E, C3, and our reflection operation. For E, we have, of course, just the unit matrix, right? It's unchanged. For C3, we have a matrix that looks a little bit strange, okay? But it's not that surprising. This is the general transformation matrix for a rotation. Okay? And we've already used this transformation matrix in disguise when we did the C2 operation. For a general rotation about angle theta, this is the kind of transformation matrix you would have. You just plug in the value for theta, and you get the values for these 4 different matrix elements here. This is a rotation around the z-axis, and so that's why the z-coordinate doesn't change. Okay? There's a 1 there. If we do a C3 operation, we have a 2 pi over 3 angle that we're changing by. Okay? If we stick in 2 pi over 3 for cosine of 2 pi over 3 and negative sine, etc., we get these numbers out. Okay? And one of the most important things to recognize here is that when you have a 120-degree rotation, the x and the y coordinates after the rotation, each of those coordinates depends on each of the coordinates before the rotation. The x and the y's are linked. They're coupled together. They cannot be decoupled. And that's why we have a 2 by 2 block matrix here. Right? In the C2 example that we had before, you rotate 180 degrees and you just change x to negative x and y to negative y. They don't have any coupling in a C2, but they do have coupling in a C3. So that's why we have these off-diagonal elements now, okay? Because the eventual x and y coordinates depend on both the original x and y coordinates. We'll come back to this in a second. Okay? So this is actually the C3 transformation matrix. And then we have the reflection matrix. Okay? And all we're going to do in the reflection is we're going to take one of the coordinates and bounce it through the plane. The other two coordinates that are in the plane stay put. And we'll just choose the y coordinate to change. It doesn't matter which one we choose, as long as it's not z. Because z is along the principal axis here. Okay, so what does this give us? Well, if we try to block diagonalize these three transformation matrices, we have the situation that we can make a block that's 2 by 2 and a block that's 1 by 1. Okay, we can't make three individual 1 by 1 blocks anymore because we have this coupled situation from the C3 rotation. So we have a 2 by 2 and we have a 1 by 1. The 2 by 2 corresponds to the x and the y, and the 1 by 1 corresponds to the z. Just as before, we can take the character of the 2 by 2 and the 1 by 1. The character of the 2 by 2 is, remember, the sum of the elements along the diagonal. So the sum of these two is 2, and so that's why we have a 2 under the E operation. The sum of these two is negative 1, and so that goes here. And the sum of these two is 0, and so that goes there. So we call this an E irreducible representation because it's a 2 by 2 matrix, right? 2 by 2 matrix. And it always is going to have then a character of 2 under E. The other two characters corresponding to the other two symmetry classes are just read right off of the summation along the diagonal. Okay. So that immediately gives us from the transformation matrices E. And if we look at the Z, the 1 by 1 in the green here, we have, of course, a character of 1, a character of 1, and a character of 1. That's the totally symmetric representation. Okay. That's the A1 that goes up here at the top of the table. 1, 1, and 1. Why is it not called the AG? It's because there's no inversion center in this molecule. Right? So G and U labels only come to be when you have inversion centers. If you don't have inversion centers, there's no reason to use G and U because there's no even and no odd. Okay? So in this case, we just call it A1 because it's symmetric with respect to the principal and it's symmetric with respect to the next symmetry operation over. How do we get A2 to complete the table? Well, we can do that by using the orthogonality rules. Right? And the fact that A2 has to have a character of 1 under the identity operation. So that gives us E in the red. It gives us green, the A1 in the green matrices there. A2 comes about by using orthogonality and the fact that the character under E has to be equal to 1. So we can run through that very quickly. The easiest thing to do is to look at the difference between A2 and A1. Right? Remember that the sum of the products over all of the symmetry operations has to be equal to 0. Right? And so we have 1 times 1 plus 2 times 1 gives us positive 3 so far, plus 3 times negative 1 gives us 0. So 1 plus 2 plus negative 3 is equal to 0. And you could do the same thing down here as well. Right? You can do 2 plus negative 2 plus 0 gives us 0. Okay? So that's how we would build the A2 out of the other two symmetry, or the other two irreducible representations. and generate the entire character table. Okay, so just some notes about this and how it's different than the C2H, okay? Just to cement these points. The C3 and the C3 squared are identical after doing a C3 operation. Right? You can do a C3 and you can convert those two into one another, and so they're in the same class, right? And they're grouped up here in the table as two C3 operations. The three mirror planes are identical after 120-degree rotations, right? In other words, after C3. And so they are also in the same class. We call those the three vertical mirror planes, and we group them up here into one column. Okay. We see the E representation here. This is immediately telling us it's a two-dimensional representation. In other words, in this case, X and Y are coupled together, and so we have a 2x2 matrix. That gives us a character under E of 2, and for this particular point group, it mixes X and Y. That's not necessary, right? It could mix X and Z, it could mix Y and Z. If you see a T, right, that means it's a 3x3. That means the X, Y, and the Z are all coupled together. And there are various rotations that you could imagine that are going to cause that sort of situation. Okay. And the way that we think about this is that when we see the full character table, here are the functions, right? When you see functions that are in parentheses like this, this is telling you that the X and Y together transform like an E. Okay? The X and Y are inextricably linked together in this case. So there's no sense in thinking of them as just X or Y, but you think of them as X and Y together, or Rx and Ry together. Rotations around those two axes at the same time give us an E symmetry. Okay? When they're not in parentheses like this, right, this indicates that you can, it's either the X squared plus Y squared or the Z squared. You know, it's not linked together in the sense of having a 2x2 or 3x3 matrix. And you can just quickly look through this table and make sure that it obeys the rules of the character tables that we've already described. Right? Orthogonality we've already shown, but you can show that the summation rules along the column and along the rows are also met. And they are. Right? They sum to the order of this particular point group, which is 6. Any questions about this procedure? Yeah, sure, the orthogonality. So remember, the orthogonality is that we're going to take the sum of the products of the individual characters, okay, and they better add to 0. So let's do that for A1 and A2. We take the product of these two, which is just equal to 1. Right? We sum these two, but we have to do it twice because there are two operations. Right? So that's 1 plus 1 plus 1. That's 3 so far. And then we have negative 1 times 3. So that's 6 terms altogether in our sum, 3 of them positive 1, 3 of them negative 1. Gives us 0. Yeah. Other questions about this? It will be a bit perplexing at first. Okay, it's totally normal. When we start using them to look at molecular vibrations, for example, it'll become much clearer and more familiar. So no worries at this stage. Other questions, though? Okay. Okay, so let's do a little summary here, and then we're going to look at our first application of symmetry, and that's what we're going to finish up on today. Each molecule has a point group, as we know. Okay? The point group contains the full set of symmetry operations that describe the molecule's overall symmetry. And we know how we can assign point groups at this stage. We can use the decision tree, or we can use whatever logical decision-making process we want. The idea is we want to get from the point of using the decision tree and relying on that to just intuitively seeing what the point group is of the molecule. Okay? And I think the time was something like less than 10 seconds is what we're shooting for. Okay? Can be done. Character tables, which we just showed examples of. We showed how to build 2 of them. Okay? We kind of cheated because we went to the final answer and then we backtracked. But this is just for teaching purposes, so hopefully it's easier to understand. Okay? Character tables show us the complete set of irreducible representations and how those transform under all of the different symmetry classes of the group. Okay? So it lists all of the symmetry information in a convenient tabulated form. And we're going to use the symmetry tables to understand bonding and spectroscopy. Again, if you want more information, then this is the book that I used back in the day and would be a good reference book even now. Okay? This is one of the classics in the field. Okay. Let's use symmetry. Our first application of symmetry is pretty straightforward. And in fact, we don't need the character table at all to do this. We will need the character tables extensively in the next class to look at molecular vibrations. The first application of symmetry is an incredibly powerful concept. So we can immediately use symmetry to tell when a molecule is going to be chiral. Okay? There's just a simple rule when you can have a chiral molecule and when you can't. To be chiral, a molecule cannot have an improper rotation axis. If it lacks an improper rotation axis, it is chiral. What does that mean for our point groups, right? What point groups lack improper rotations? We have to be in the C1, the Cn, where n can be anything, or the Dn, where n can be anything point groups, right? The pure rotation point groups. We can't have any mirror planes because if you have a mirror plane, remember a mirror plane is the same thing as an S1, an improper S1 rotational axis. And you can't have an inversion center in your molecule and be chiral because according to our rule, and we remember that inversion is the same thing as 180-degree rotation followed by a perpendicular reflection, otherwise known as an S2. So you can't have a mirror plane, you cannot have an inversion center, and you can't have any of the other possible S axes. Okay. So let's look at a bonehead example of chirality here. This is the mirror image of this particular tetrasubstituted methane with itself. Okay. We know already, we've assigned the point group of this molecule, it's C1, right? It has no symmetry. It's asymmetric. It only has E, right, as the operation. And if you take its mirror image and you try to superimpose them, of course, it doesn't work out. Okay, so chiral molecule, because it's a C1. Okay. Let's look at a second example. So this one's a little bit harder, but you could sit there and you could convince yourself that this is a D3 molecule. Right? It has no reflection planes and no inversion center in it. But it does have a threefold axis of rotation that's coming out at you. And it does have perpendicular C2 axes, of which there must be 3. Right? It's a D3, and that tells us right away, because it has no S operations associated with it, it must be chiral. So here's the molecule and its reflection. You try to superimpose them, and you cannot do it. Okay? So there are many rules like this. There are rules that pertain to chirality. There are rules that pertain to other optical properties, like whether a material can be second-order nonlinear material, whether molecules have certain kinds of optical activity. Many different things can be immediately described as absolute yes or absolute no based on just symmetry. And that's why it's so powerful. Okay? So next time what we're going to do is we're going to pursue our second application of symmetry where we actually use the character tables in detail to understand vibrations.